Valves are used to control the flow of fluids in process systems. In order to meet the needs of a process system, some method of changing the positions of valves is needed. Some valves can be operated with hand wheels or levers, but some valves have to be opened, closed, or throttled frequently. Manually positioning valves in these types of situations is not always practical, so instead of hand wheels or levers, actuators are used to position the valves. We'll define an actuator as a mechanism that moves or controls a device such as a valve. Actuators reduce the need for operators to go to every valve that needs repositioning and operate the valve by hand. When actuators are used, valves can be repositioned from a central remote location, such as a control room. This is very important in processes where a number of valves have to be repositioned accurately and quickly. There are three basic types of actuators: pneumatic actuators, hydraulic actuators, and electric actuators. Pneumatic actuators use air pressure to produce motion to position a valve. They're probably the most common type of actuator used in process systems. Actuators that are powered by a pressurized liquid, such as hydraulic fluid, are called hydraulic actuators. Compared to pneumatic actuators, hydraulic actuators of the same size are usually more powerful. Electric actuators use electricity to produce motion. They usually fall into one of two general classifications: solenoid actuators or motor-driven actuators. This type is often referred to as a motor operator. Regardless of the type of actuator that's used, valves with actuators are normally part of process control systems. From a control room, valves with actuators can be quickly and accurately positioned to deal with frequent flow changes. Valve actuators operate and position valves in response to signals from controllers. Controllers are part of the instrumentation systems that monitor plant processes and respond to variations in the processes. Basically, a controller is a device that receives an input from another part of the instrumentation system, compares that input to a set point, and sends out a corrective signal to regulate the value of a process variable, such as temperature, pressure, level, or flow. Generally, actuators are used with valves that are designed for throttling or regulating flow. Valves that are used to automatically throttle flow are generally referred to as control valves. However, some on-off or isolation valves may also require actuators. Although these isolation valves may require actuators, they're not commonly referred to as control valves. Control valves work in basically the same way as manually operated valves. Control valves can be either linear, that is, the stem moves the valve disc up and down, as in globe valves, or they can be rotary, which means that they're positioned by rotation. Butterfly valves, which open or close with a 90-degree turn, are examples of rotary control valves. This is a globe-type control valve. It has the same basic parts as a manually operated valve, including a valve body, a disc, a seat, a bonnet, a stem, and a packing assembly. Control valves also have parts that may not be on manually operated valves. For example, control valves, like this one, generally include guides that align the valve stem and disc with the valve seat. These guides help ensure precise control when the valve is opened and closed. The upper stem guide on this valve is housed above the packing inside this part of the packing assembly. This is the lower guide, which is held in place by this part of the valve called a cage. Part of this cage, along with other valve parts, have been cut away to better show the valve's construction. The cage is a hollow cylinder containing openings. When the valve disc is moved away from the seat, fluid flows up through the seat, through the cage openings, and out of the valve. In this topic, we discuss general classifications of actuators and what type of power each actuator uses to move a valve. We also looked at the function and design of control valves. Now let's stop and try some practice questions. Valve actuators operate and position valves in response to signals from controllers. Controllers are part of the instrumentation systems that monitor plant processes and respond to variations in the processes. Basically, a controller is a device that receives an input from another part of the instrumentation system, compares that input to a set point, and sends out a corrective signal to regulate the value of a process variable, such as temperature, pressure, level, or flow. Generally, actuators are used with valves that are designed for throttling or regulating flow. Valves that are used to automatically throttle flow are generally referred to as control valves. However, some on-off or isolation valves may also require actuators. Although these isolation valves may require actuators, they're not commonly referred to as control valves. Control valves work in basically the same way as manually operated valves. Control valves can be either linear, that is, the stem moves the valve disc up and down, as in globe valves, or they can be rotary, which means that they're positioned by rotation. Butterfly valves, which open or close with a 90-degree turn, are examples of rotary control valves. One of the most common types of pneumatic actuators is the diaphragm actuator. In a diaphragm actuator, air pressure acts on a flexible diaphragm to position a valve. A single-acting diaphragm actuator is called single-acting because air pressure acts on only one side of the diaphragm to position a valve. A typical single-acting diaphragm actuator consists of a casing, a diaphragm, an air supply port, an air vent, a spring, a stem, and a valve position indicator. The indicator shows the position of the valve. The center of the diaphragm is supported by metal plates, and the outer edge is sandwiched between the rims of the upper and lower halves of the casing to form an airtight seal. This arrangement divides the casing into two chambers, an upper chamber and a lower chamber. The upper end of the actuator's stem is connected to the metal plates in the diaphragm, and the lower end moves the valve disc. When the actuator receives a signal from a controller to close the valve, air pressure is applied to the upper chamber, the diaphragm and the actuator stem are pushed downward, the spring is compressed, and the valve closes. Air in the lower chamber is exhausted through the air vent. When air pressure to the upper chamber is reduced, the spring moves the actuator stem upward, and the valve opens. These actions make stem movement and therefore valve position proportional to the amount of air pressure applied to the actuator. Controlling the applied pressure enables the actuator to position the valve anywhere within the limits of travel for the actuator. This type of actuator can be called an air-to-close, spring-to-open actuator because air pressure moves the stem to close the valve and a spring moves the stem to open the valve. This means that if air pressure to the actuator is lost, the control valve connected to the actuator will fail open, since spring pressure would raise the stem and open the valve. A single-acting diaphragm actuator that's designed to close a valve or fail closed when air pressure is lost looks like this. As you can see, it's very similar to the actuator we just looked at. During operation, air pressure is fed into the lower chamber. This causes the diaphragm to lift, which expands the spring, raises the stem, and opens the valve. When air pressure is reduced, the spring pulls the diaphragm and the stem downward, closing the valve. A control valve using this kind of actuator is said to fail closed because if air pressure is lost, the spring in the actuator will close the valve. A diaphragm actuator with an air line to only the lower chamber is typically an air-to-open, spring-to-close type, which causes a control valve to fail closed. An actuator with an air line to only the upper chamber is typically an air-to-close, spring-to-open type, which causes a control valve to fail open. By controlling the applied pressure, either of these actuators can be used to position a valve anywhere within the limits of travel for the actuator. Regardless of how they operate, single-acting diaphragm actuators are usually represented on process piping diagrams by this symbol.